Hi, my name is Patrick. I'm a teacher at Pima Community College. I want to tell you about a job I was on when I was a carpenter in the early 90s or late 80s. I can't remember, somewhere around there. And so you can see in the middle here, there's this driveway, and it goes in here and there's a little circle in there. They couldn't figure out how to lay this out. And I'm going to tell you how I figured it out. This part over here on the right is the new part we built, and it has this little cutout that's kind of a circle shape. And as you go around, you can see, so the cars come in, they drive around a little circle. And while we were building the building, the hospital was still going. There's an emergency room and there's parking, and so their cars are going through this the whole time we're building the building. And they were trying to figure out, how are we going to lay out this circular cutout on our building before we pour the concrete. And the only way they could think of was to, where this bush is in the middle, to build a scaffold there, like 3 stories high, and then pull a tape sideways to lay out the cutout there to cut off the metal flooring so they could pour concrete into it. Which would have made, they would have had to get permission from the hospital to block the traffic. Where would all the doctors park? It would have taken a day off of for all the laborers to build the scaffold, to raise it up there. They'd have to drop a plumb bob down to the center and then hope it's accurate and pull a tape across to 1 level, 2 level. I think there was 3 levels there that you had to pour. And that would have been really expensive, and that's the best they could think of until I gave them a different idea. So here's a still picture of that cutout. And so here, the green dot here is a known center or the radius of the circle. They would have had to pull across to cut out the bottom level, a 2nd level, and a 3rd level to cut out the metal flooring that you pour the concrete into. And they were thinking of building a scaffold, 3 sets of scaffold, and dropping a plumb line and then pulling a tape across to the places. So that was their best idea. They had a job trailer over here. They had more than 1 engineer. They had college-trained people trying to figure this out. They had months to figure it out, and they told me about it, and I came up with a solution pretty quick. The day they told me about it. So here's the problem kind of drawn in a more schematic way. You got this blue line is, you need a radius cut out of here. And you know how far it is across from the center of the radius to, that's all that's on the plans, is these dimensions. And this red line is a known benchmark inside the building that we could use to pull measurements off of, but the plans didn't have this dimension coming back this way, or here, so we were sort of left to our own devices. So what would you do? There's 3 levels of it, and I don't remember the dimensions, but I'm guessing that the radius might have been 30 feet to the bottom level, 32-foot radius to the middle level, and a 34-foot radius to the top level. So are you thinking of what you would do? It was easy to figure out if you got a straight line here. This would have been easy to figure out because it's a known distance from the benchmark to the radius point, either from the east-west or from the north-south. The radius point was known. So if you know it's 34 feet, then you just pull back whatever the full distance is and subtract the 34, and you would know what distance. So you could have start cutting the metal right there to form the floor of what's going to become the concrete. And so they knew how to get that one started. They probably already had it laid out before I came on the scene. The problem was, once you get a little further out here, now you've got an angle. The angle is changing all the time. It's still 34 feet for a radius, but like, how would you decide where to cut here if you come a certain distance away from this red line or this red line. I mean, you know, as you go further and further to the north that the numbers are going to get bigger, and you know as you go further and further to the east that the numbers are going to get smaller and smaller. But they didn't know how to figure this out by pulling distances from inside the building. So have you figured it out yet? What can we do? Well, my idea was to choose any convenient number. So you'd want to do like 5 feet, 10 feet, 15 feet, 20 feet. And so that you could have a nice consistent curve. I don't know how many feet increments I graded it in. I asked them like, how far apart do you want your increments? And they told me, and so that's what I did. So say at 20 feet, and then you have a radius of 34 feet. So there's your hint. Can you figure out what I'm going to go to next? And this is just high school math. This isn't trigonometry. You could have done it with sines and cosines, but there's an easier way also. Yeah, you figured it out. It's the Pythagorean theorem. So if you know this length and you know the hypotenuse, then you know that one leg squared plus the other leg squared is going to equal the hypotenuse squared. So I did this. I had to do these calculations like 30 times from here to here. And then let's say for x you get 21.63804 or something like that on your calculator. Then you have to change that into inches and then 1/16 of an inch. So it took me some time. It took me basically all day to do the numbers for this, and maybe all day the next day to lay it out. So if you're just as an estimation, if you know this is 34 feet and you just decide to come 20 feet across, then you can, by squaring and then doing the square root, you can figure that x is going to be something like 27.5 feet. So now you can do all the layout from inside the building. You don't have to close off traffic in this circle. The doctors can still go in and out to their parking garage. You don't have to build a scaffold here. You can do all the layout from inside the building where we are working. So you got your known benchmark back here, you got your known benchmark back here. You know how far it is to the from the benchmark to the radius in the east-west direction and in the north-south direction. So now if you know this distance, you just subtract 20 and you'll get this distance here, and you can lay it out on the metal. And you know this distance, so you subtract 27.5, so you can get this mark. You can make your your east-west crosshatch and your north-south crosshatch, and right where they cross is your mark. You make your mark, and that's where the iron workers are going to come and cut the tin, and you make as many marks as you want until the iron workers are cutting a nice, perfect radius there. So that's how I lay that out for the Evergreen Hospital job. And I don't need to tell you that once they that impressed them. It saved them lots of money, and so math saved the day. That was the height of my career as a carpenter. Before then, I was sort of slogging around down in the mud, and after that, I was like the guy with the pocket protector and the pens and looking through the instruments on the tripod. So I got a lot of respect from bringing math into the situation there. If you have any questions about Pima Community College or the building and construction trades, I'm going to leave a link down in the bottom, and hope to see you at one of our building and construction trades classes, one of our math classes. I teach adult ed, math, and building and construction trades. Hope to see you soon. My name is Patrick.